There we go. This is where we're at. I think we're in really good shape. I think we started with like 26 or 27, and we have 19 right now. Yeah, congrats. We're almost two-thirds of the way through Analyze, and then we just got the fun part coming, improve and control. So the, this week we'll have a couple of pieces of homework. One is going to be a normality test, which I'm going to show you right now. And then the other one's like about a minute and a half of using the data analysis tool to do ANOVA, which we're going to talk about in a bit. And then I think we got a week off from homework. Then we go into correlation, aggregate. Down the stretch we go. There's only a handful left. So at this point, I think just put your head down and try to enjoy some hypothesis tests like crazy today. Um, Let me start with normalities. This is going to be the homework. So the thing is, we looked at a couple data sets, different sets of data. One was my weights, right? And it was like 800 pieces of data. And then we looked at the weather, and there was about, I don't know, a million probably pieces of data in terms of temperature on a certain day. Now, what if you only have like from January to looks like August of 2006? And I want to see if I want to try to do some hypothesis testing. I want to try to make the data talk. Well, I have to know if you look at this chart that you guys have been looking at for a few weeks, largely I got to know if my data is normal or not, right? So how can I tell? Because I can go ahead and I guess I can draw a bell-shaped curve and see if it's normal, or I can do this cool test called a normality test. And I just want to take you through it. So I really only have, let's see how many pieces of data I got there. Um, I got 20 pieces of data, so I just want to know, is it normal? Bell-shaped curve, with the middle of the bell being the average or the mean, and then equal number of data points on each side. So this is a very useful tool because once I figure out if my data is normal in control, then I can use one of these beautiful hypothesis tests to make it talk, right? And the thing we're going to use to determine whether it's normal or not is we're going to compare this data to a perfect bell-shaped curve, all right, using a tool called a correlation, which we're going to cover next couple of weeks when we get into the improve phase. Well, is there a correlation? Is it closely correlated, this data, to a perfect bell-shaped curve, like my weight, for example, right? So here's the steps. This is the homework. First thing we're going to look at, here's the data. First column is rank. And what we're going to use is a function called equals rank. And it's the third one down there. You grab that, double click on it. And then, of course, it's going to ask us some questions. The first question it's going to be asking me is, give me a number. So I'll take that first number, then a little comma. And then the next thing it's saying is ref. And all it wants there is it wants the whole range. So I'm going to highlight all of these cells. And then I have to lock them in. So I'm going to put a dollar sign on both sides of B21, on both sides of the B on B21, because I want to stay there, right? I don't want the calculation to go to the next number. Locks it in, kind of, right? That's what it says here it's right here on the right, guys, where it says lock in range values. So I'll put a dollar there and a dollar here. And then it asks me what order, and I'll get an option between descending and ascending, and just click on ascending, hit enter. Well, of course, doing all the yapping and I messed it up. I gotta get rid of the and sign. Sorry about that. There we go. And I get a rank of 8, and then I just double click that little box bottom right. Boom. Got all the ranks. Then the next step, so I did the ranks. Now I'm going to get into index, right? So I'm going to use, really important here is pay attention to the parentheses and all the exactly the way I have it here. So here I'm going to go equals parentheses, and the first thing it's asking in this box on the right is the rank. So I'm going to the rank I just calculated, the 8 minus sign, the fraction 3/8, and then another parentheses. And then you'll see there's a divide there, and then another parentheses. Then n is going to be the number, which is going to be 194, plus sign, 1/4, parentheses. And I get that beautiful number. Double click that. All right, then next column, number 3 is z-score. So I'm going to go use equals, and it says to use normal.inv. So as soon as I hit equals, it's going to give me all these choices. I'll grab normal INV. And then it's going to tell me that I'm comparing this to a perfect bell-shaped curve, which has a mean of 0. Because don't forget, when we do the bell-shaped curve, if I have a perfect bell-shaped curve, then the mean is going to be 0. And then I'm going to do the standard deviations to the right and left. 1, 2, 3, -1, -2, -3. So in this case, I'm going to plug in 0 for a mean, comma, standard deviation of 1, close parentheses. Oh, I apologize. I got to stop talking, right? And when I have to do it from scratch. Now I'm flustered. Normal inventory, and it's going to say mean is 0. I got to grab the index. That's what I forgot, right? So I was yapping. Go. This is embarrassing, people. I've done this a gazillion times. You're saying, how the hell are we going to do the homework? Probability, comma, 0, comma, 1. Bing! And double click all of them. All right, now I want to draw. So you notice that the yellow, the R correlation filled in at 0.97. So we're going to do a lot more of this, when we get into the improve phase. But a perfect correlation, it means that, like in other words, one thing I might want to know is there a correlation between my weight and my blood pressure? When my weight goes up, does my blood pressure go up? When my weight goes down, does my blood pressure go down? And the perfect correlation between two things like that is 1.0, 1, whole number 1. If I get close to a 1, that means I got a pretty good correlation between those two things. And if I have a R correlation closer to 0.0, so it's not near 1, that means I don't have a good correlation. So what we're asking here is this data, these 20 pieces of data, how closely correlated is it to a perfect bell-shaped curve? All right, because then that means that my data is normal data, and I can use any of these hypothesis tests that I want. So what I'm going to do next is we're going to draw a graph, highlight weight, highlight z-score, insert data, go to data, insert a, what am I, I'm sorry, go to insert, recommended charts. I'm having all kinds of problems today, aren't I? Do it again. Grab weight, z-score, hit insert, recommended charts. And the first one is the one I want. And this is what it looks like. So next thing I'm going to do on this chart is I'm going to click on one of the dots, right click, add trend line. And you can see that trend line up here. So largely, if this was a perfect bell-shaped curve, perfectly normal data, then all these dark blue dots, they would be on the line. So we're not that far off. There's a couple of them that are off the line a little bit, and we're going to get into measuring that when we get into a little bit deeper into correlation stuff. But basically, what it tells you is I can go ahead and use this, make some conclusions with this data using hypothesis testing, make it talk for me, ask questions of it because the data seems to be normal. So even though I struggled, is because I was yapping a lot. That's the home part of the homework for today. Um, the second part of the homework, I'll show you in a couple minutes, takes a minute or two. So let's get into a little bit more. Any questions about the homework first, guys? Again, if you're behind in the homework or if you need help with the homework, all you do is reach out to me and I'll get you through it. This one's just, it's more than anything, it's just, keeping an eye on making sure you get the parentheses right. Don't talk too much like I do. Um, it shouldn't be too tough.
Bill, real quick,
Yes.
can you explain what rank and index are with that data?
So the rank, basically, I'm going to be ranking from, let's see, what's number two here? If they're ties, there's a couple of ties on there, but basically we're ranking, if I have a lot more pieces of data than I actually see 1 through 50 or whatever. So I'm not sure the formula off the top of my head. I can get that for you in terms of how each one of them comes up. 189 would be ranked the lowest amount. So that's the least I weighed. I'm just not sure how the ties work. Yeah, 192 is 5. Well, yeah, I got to get back to you on that, Ryan. Good question. And then the index, I'm taking whatever that calculation is, and then the 3/8, and I'll get that for you. I didn't cover that. I didn't prepare for that, so that's a good question. I wrote it down. Way to keep me out of what do you call that mode? Where you just kind of go. Let's see. So next, let me show you the other home. I'll stick to this t-test. Ryan, I know I didn't satisfy your question, but I will get that to you.
Yeah, no problem.
Yeah. All right. So now we're going to talk about another one of these tests, and it's called the one sample t-test. So if we look at the chart, we're going to cover it in the PowerPoint. The PowerPoint's going to be very brief today because we're going to cover most of it here. But it's talking about continuous data, which is data that we measure. Remember that discrete data is data that we count, like votes or defects or things like that. We have to have a normal distribution. We're looking at the average or the mean. We have to have one sample, all right? And an example that we're going to use to go through it, and it's the same steps that we covered last week, and just trying to get those ingrained in your head. So this one is a typical supermarket trip, takes 22 minutes. So we want to test it out. We selected 50 shoppers and we timed them, how long it take them to go in, get their stuff and come out. And the average mean shopping time was 25.36 minutes. So the supermarket's claiming that it takes 22. So one thing we want to know is that 25.36 minutes statistically significantly different than the typical supermarket trip. It's all we can tell, right? Is it statistically significantly different? And we have a standard deviation of 7.24 minutes for those 50 shoppers. So that means if I have an average time of 25.36, then the average away from that 25.36 was about 7.24 minutes. So we're going to use a 0.1 level of significance, which is a 90% confidence. Is there evidence that the mean shopping time of these 50 is different from the claimed value of 22? So step one, I got a problem statement. That's it. Step two, I have two positions, right? And the null hypothesis is always going to be the status quo. So yeah, there is no difference. And the alternative hypothesis is yes, there is a difference between a statistically significant between 25.36 and 22. And then we have to figure out, again, ahead of time, at what confidence level we want to look at it. So zero point 0.1 is the same thing as 90%. So we're going to be 90% sure with our answer. And then, of course, for every single one of these tests, there's a test statistic that we have to generate. So in this case, here's the formula for it for this one sample t-test. And you can see that we have the average of 25.36 for this particular, those 50 shoppers, minus the average, 22 minutes of a typical supermarket trip, divided by the standard deviation, which is divided by the square root of the number of people that I tested. And I come up with a test statistic of 3.28. And I know I have to compare that to a critical value. And the critical value I get from a shot. And so largely what the chart's going to be asking me here is I know I'm going to be in the 90 or 0.1 confidence level. Confidence is 90, alpha level 0.1. And degrees of freedom, if you remember, is a sample size minus 1. 50 minus 1 is 49. So the best number I can come to with this chart, 1.684. Or I could use 1.676 actually. And those are my goalposts, if you remember. So if I draw it out, there's the 1.7 as the goalpost. And anything to the left or the right is the rejection region, which means I can reject the null hypothesis, meaning that what I just tested is different than typical, the average. And we can see that our test statistic is 3.28, way over to the right in our rejection region. Again, if I want to look at 99% level of confidence, I'd go over here to this fourth column, down to the same number of degrees of freedom, and my goalpost would be set at 2.704. So still, I'd be in the rejection region, but this line where it says 1.7 would be moved over a bunch on both sides. But that's basically the same thing. You're gonna see like, I don't know, 8 or 10 different hypothesis tests when we get into the PowerPoint. And it's all the same steps. It's just, are we looking at the mean? Are we looking at a variance? Are we looking at proportions? We have to just understand and recognize what our data is to pick the correct test. So that's another hypothesis test. And then the last one, this is a little bit of homework, nothing much. This one's about, let's say I have 3 shifts. And what I'm measuring here for the second shift is in column 1, third shift is in column 2, as you can see, 12 a.m. to 8 a.m., and first shift is in column 3. You can see that I have 36 pieces of data, so my degrees of freedom are going to be 35. And all I want to know is, and when we talk about ANOVA, what we want to know is there a difference in stress level within the shift and between the shifts at the same time? So there's the formula. I went ahead and nothing better else to do, so I went ahead and did that, as you can see here. But I hope you never do it. I hope instead you'll use your data analysis pack to do it. Largely what we're going to find out here is that my test statistic, and that's the one that came out of the formula, is 27.58. And I know I have to go to a table to find out what my critical value is, so I can compare it to. Because basically, the null hypothesis is going to be that all of the shifts are the same, right? The average stress level in all 3 shifts is the same. That's the status quo. And my alternative hypothesis, the only thing that I can, the alternative hypotheses are not equal, right? So, and my only objective is to reject the null hypothesis if I have enough information. So let's take a look at a quick way of getting exactly that same 27.58 in that 3.23. I'm going to use the data analysis pack. And we're looking for single factor ANOVA. And it's going to ask me for first input range. I'm going to include the headers in this. Just grab all my data. And I'm going to type in labels that are in the first row. We'll use a 95% confidence level. So the 0.05, I'll leave that to where it is. And it's going to ask me where I want to put it. And I think I'll put it maybe L24. And bingo, presto, I get this. And if you look at F crit, that pretty much equals, that's F crit is what I took out of the table. 27.58 is what I, after all this gymnastics. And I know that my critical level, this is way the heck out of into the rejection region. So I know that I can reject the null hypothesis, which means that, yeah, there is a difference in stress level within and between the three shifts that we're running. Now I can go ahead and say, all right, what's going on? I can dig into the root cause of it, the whole 9 yards, but I know that there's a statistically significant difference. So that is ANOVA in a nutshell. Ryan, anything there? Anybody else? We good? All right, just a quick, so the homework is going to be just generate that table using the ANOVA and then go ahead and go through the normality testing. With that, 22 minutes in, and then we're going to fly through the PowerPoint today. So last week, we talked about multivariate analysis, got class of distribution, sampling techniques in inference, general concepts and goals of hypothesis testing, practical versus statistical significance. We're looking at statistical significance. We looked at risk, alpha and beta risk, and confidence levels, all that, and then how to read tables. Today, we're going to kind of review a bunch of the stuff we just did, thankfully. Testing for normality, testing with normal data, tests of equal variance and z-tests, and then a couple of these we already covered. One-way ANOVA, one sample t-test. So we'll fly through them. And then next week, this is no homework next week, but we're going to get into hypothesis testing with non-normal data and also with discrete data. All right, so let's talk about normality testing real quick. Let me blow this up. So we want to know whether the data is normally distributed, because it's going to impact which test we use, how it's analyzed, how it's interpreted. We got to know that our process is stable, right? Can't be all over the place. And we usually introduce that in the measure phase, but normality is not a given. There's some functional or physical limitations that restrict the ability of normality, like a pitcher can't throw a baseball negative distances, phone call duration can't have a negative time. So obviously I have to use other tests when I'm doing that kind of measuring. Kind of what we just did. We run a normality test on the data to see if it's normally distributed or not. And we're comparing the p-value versus the alpha level. Basically what we're looking at is we draw the line and how close to the line are our data points. And again, the reason I would do this test is if I have a smaller sample, I don't have a lot of data, because over time, if I collect more data and I work my process, it's generally going to become normalized, like my weight, like the weather, like things that we're constantly measuring. Or normal data. So here's the steps again. I apologize for the redundancy, but it is what I think it's good to hear it over and over. State the null, determine the alpha or confidence level, collect some data, select the proper test. That's probably the hardest thing to do. Run the test, and then determine whether to reject the null or not. And these are the ones that we've covered so far. We're going to touch on a bunch of them, a bunch more of them. So let's look at tests of equal variances. There's again the notation. So sometimes we want to check whether the variances of two populations of interests are statistically significantly different. So we use the test of equal variance, where the null hypothesis would be there's no difference between two populations and their variances, kind of like very similar to what we did with the shifts and the stress levels. And then the alternative hypothesis is always going to be, yeah, there is a difference. No difference, there is a difference. And we could use it as a prerequisite for other tests, because other tests, there's, some of the criteria might be, all right, this test is for populations with unequal variances. All right, well, I got to do ANOVA to figure that out, like I just did with the stress test. So let's go through some of these tests. So an F test can be used to compare the variances of two samples. Again, the steps on the left. So continuous data, instead of looking at average or mean, like the shopping time or the average of the weather, we're looking at variance between two different sets of data. Okay, two samples. Again, the null and the alternative are going to be the status quo and not the status quo. And this is known to be extremely sensitive to non-normality. So that's next week. We'll talk about the Brown-Forsyth test if I have non-normal data. So two samples and decisions. There's the test statistic for it. We're going to compare that to a critical value from an F table, and then tells us when we're going to reject the null or not reject the null. Same idea. Pretty simple. And then Bartlett's test is used to test if K samples are from populations with equal variances. Some statistical tests, like the analysis of variance, assume variances are equal across groups of samples. Bartlett's test can be used to verify it. Never used it. Nor have I ever used Levine's test, which is inferential statistic used to assess the equality of variances for a variable calculated for two or more groups. None of this is on the exam, guys. There's no questions on the exam that ask you which test you use. I think the big thing is understanding the steps, understanding that I need to kind of figure out, or which equation am I going to use, and where do I find the table that I compare it to? Brown-Forsyth, again, a statistical test for the equality of non-normal group variances. So non-normal group variances. And unequal variances are usually the result of differences in the shape of the distribution. So I'm testing two things, and one of them might have extreme tails, a lot of outliers because the process just isn't normal. It's just not stable. It might have multiple modes in some cases, and yeah, beyond the scope of our class. T-tests. This is our favorite. It's the simplest normal distribution with the mean equal to 0 and the variance equal to 1. So each to the right and to the left is a standard deviation each. It's how many standard deviations an observation is above or below the mean, or in the case of when you graph it, to the right or the left of the mean. And we want to use lookup tables to find the population between U and X. Z-test, one or two sample. We've done some of these last week. Continuous data, we're looking at the average. It's normally distributed. One or two samples, a small sample size, and the standard deviation is known. Same idea, the null and the alternative. And there's a beautiful Z statistic. effectively transforms the actual data into standard normal units. So that's 0, -1. Instead of my weight, 184, I think the average was over the last 2 years, and then the standard deviation being 4 pounds, maybe, I think it was. So it'd be 184. The first, that number one would be 188, 192, 196, and the same thing on the lower weights. And this is the calculation actually that we used last week when we were looking at the weather. And here's the decision rules, kind of the same, so again, confidence level, alpha level, 0.05 for alpha, 95% confidence. So I want to know where to put the goalposts. And if my p-value is greater than 0.05 or 95%, I fail to reject it. And if it's less, then I can reject it. One sample t-test, the mean of a single sample against a target, one piece of equipment, supplier A's quality, supplier B quality, performance of products before and after a given process, shopping times, also known as a student t-test. And remember, the student t is it's a type of distribution where I can, even though I don't have every whale as a sample, I've only sampled a small number, less than 30, because I can't go out possibly and weigh them because I want to know the weight of whales. It's a way to soften the impact of the outliers, like a pregnant whale or a malnourished whale. So the t-test is a student t is a way to I can trust smaller numbers of data. And this looks familiar, right? Same, there's the criteria, continuous data, normally distributed, one sample. I'm comparing a value versus a mean. So comparing 25 minutes shopping to 22 minutes or whatever. A small sample size. This one here, actually, we had 50, I think, shoppers in ours. The population standard deviation and variance aren't known. The sample standard deviation and variance are used. So we had that, and we knew that the standard deviation was 7, I think, 7 minutes for shopping. And it's preferred over the z-test when sample size is less than 30. And there's the test statistic. Did it. And there's the decision making for this test, assuming confidence level of 95 or alpha 0.05. And all I want to do is reject the null. Two sample t-test. When comparing two populations, if a dependency exists, before and after. So same before and after I do a diet, before and after I take a medication. So they're paired t-tests. Variants are unknown but assumed equal. Same criteria, continuous data, normally distributed, two samples, and these are going to be, again, connected. So there's a value versus a mean, small sample sizes, population standard deviation and variance not known, sample standard deviation and variance are used. So I usually have that information. And there's the two sample pair test. Same idea. Continuous data, mean, there's a test statistic, there's a formula for it. Average difference between each pair of data. Before and after. There's the formula, compare it to a table. Chi-square. Chi-square is a statistical hypothesis test in which the test statistic follows a chi-square distribution when the null hypothesis is true. The example I'm using here is, let's say I got a study of 11,160 alcohol drinkers on university campuses. And I want to find out if A, are they binge drinkers? And two, if they are, do they seem to have trouble with the police? So if you look down the bottom there, if you add up no trouble police, there's 11,000 people have been 11,160 people, alcohol drinkers have been looked at. And all I want to know there is there a link between frequent binge drinking and trouble with the police? formula. So continuous data, I need the variance, and the variance would be one, people that have trouble with the police. The other is people that do a lot of binge drinking, right? There's a formula for it, and there's another example of when I'd use this. I'm gonna skip that. So distributions, I know we've covered a bunch of times. Probability distributions, generally the ones that I'm interested in are normal, student t, so the t's that, the ones we looked at already in chi-square. One-way ANOVA, we just talked about. This was the stress between shifts. It compares the means of different groups by analyzing variances between and within them. It's a generalized form of two-sample t-test. And one-way ANOVA compares K population means where K is less than or equal to 2. Based on sample data, the means of the three populations might look different because of two variation sources between groups and within groups. And that's kind of what we looked at with the stress levels. We want to know whether the groups are statistically different from each other. And in our case, we found out, yeah, we got a problem. There's a lot more stress on, they're not all the same. And the same exact thing we just did. There's the formulas, a lot of sum of squares. That was all the math that I did. Um, yep. See how nice we're going to math practice first, but this is exactly what I did longhand. But the modeling procedure, make sure the conclusions made in ANOVA are reliable. We need to perform residuals analysis, which we're going to cover in the improve phase. We'll get into residuals, not to worry about it now. And if the variances are not all equal, use other hypothesis tests other than one-way ANOVA. So two-way ANOVA is available for data that fits the following criteria: continuous data, mean, normally distributed, more than two means, equal variances, and more than one factor. That's we stop. All right. Any questions? Again, most of it is just focusing on, the exercise that I'm doing in math practice in terms of what you take away from hypothesis testing. And anybody problems with the homework, questions, let me know. I'll send those to you along with the recording. I got an answer. I'm going to get an answer for Ryan because I don't remember. All right. Have a great day.
Thank you, Bill.
See you guys.
Thanks, Bill.
You're welcome.
Thanks, Bob.